If you're not familiar with vLLM, vLLM is the open source standard for high throughput, memory efficient inferencing of large language models. Ultimately, it's an inference engine, but an inference engine in this fast moving space in open source AI is really critical because we have, of course, so many models coming out every week, if not every day. And we also have a lot of really expensive hardware accelerators that you're paying for, whether or not you realize it. And so it's really important that we have, efficient software that is able to get all of these, models running on all of these different hardware accelerators fast. So, vLLM, of course, gets state-of-the-art performance on NVIDIA GPUs, but part of one of the reasons why it succeeded so much as an open source project is because it's developed the right interface for serving large language models, and that's useful for both new models that are best served by matching that interface, and hardware vendors that of course match up and implement that interface. A bit about it. It's Apache 2.0 project hosted in the PyTorch Foundation with open, solid governance. It has over 80,000 GitHub stars and a very, very active community. We are basically at like 2,000 PRs a month submitted, and fortunately get through about half of them merged, which is great. It's deployed on millions of live GPU hours every single day, and many more that are happening in private. Of course, those large deployments, we get a lot of feedback and users and feature development in our developer Slack, where there's over like 15,000 members. You're welcome to join in the various special interest groups and conversations, and of course on GitHub as well. And we also have reference implementations for how the latest models of the day on day 0 should be run with vLLM on our recipes page. So I encourage you to check it out. But yeah, a bit about the project itself. We've had over 2,700 unique people merge code into the project, which is insane for a project that's only been around for about 3 years. And of course, that's supported by tons of industry giants, academic institutions, and just all sorts of companies and hobbyists and community members that make the project what it is. vLLM is kind of much more than an inference engine itself. It's a diverse project ecosystem. We have vLLM Omni, LM compressors, speculators, which you'll hear about today, and many other projects that are ultimately hosted by the vLLM project, and all serve for dealing with whatever you need for serving a model at scale, at whatever scale you need. So that's the vLLM quick overview. Now we're going to get over to talk about some of the new blogs and announcements that have happened over the past 2 weeks. So the Speculators 0.5 release came out. Obviously, we're going to have a talk on this, so I won't really go into detail, but there was a nice blog on it as well. So if you want more details after the presentation, check out the blog. We had a big release for vLLM Omni 0.22, basically matching up with the vLLM release, which is great to see from Omni. And of course, this lined up very conveniently with the NVIDIA Cosmos 3 launch, which is a very impressive world model from NVIDIA. There was actually a really fun post on Twitter about the release, and there's actually a whole video here that's generated using vLLM Omni, both image, video, and audio in the voiceover. So if it can pain you to type in this link or check out the vLLM project on Twitter, yeah, check out the video. And I also wanted to just reference, I have a screenshot of the Cosmos paper that was released. And of course, vLLM and vLLM Omni are featured as the inference frameworks for both the text side of it, and of course the Omni modality generator side. It features vLLM Omni. So yeah, it's a great proof point for how the project has matured over the certainly less than a year that it's existed, and certainly means that we placed the right bet in growing yet another project in the ecosystem. Next, I want to share a great blog summarizing a lot of work that's been happening in vLLM over the past year plus. So, if you know a bit about reinforcement learning, this is ultimately how your agentic models are being trained to be more agentic, to work in coding harnesses, to learn how to use tools and explore environments. And vLLM is a key part of that reinforcement learning process, even though it's ultimately a training process. Inference makes up the vast majority of compute during reinforcement learning, 80 to even 90%, because even though you're getting your, updates from how the model is doing and you're running it through the trainer, the majority of the time is spent in this generation phase, running the model, getting the outputs, evaluating how well it does in the environments. This takes a lot of time. And as you're generating, or as we call it, rolling out the predictions and observations from the model, you need to update those weights continuously while the vLLM server is still running. So we built in a lot of native RL APIs in vLLM. Like you can see sort of here, the init weight transfer engine, start weight update, update weights, finish weight update. This diagram here is sort of an example of how we do this for a model that does online quantization to FP8 after the weights have been transferred. Yeah, there's just a whole lot of goodies in this blog of why these various things need to be built into vLLM, and showing how it's been proven out in various RL frameworks with real training runs. So that's really cool. And another exciting announcement is the recently announced VIME, which should sound familiar if you're familiar with the Slime project from ZAI, the creators of the GLM models. They, ultimately VIME is, a fork of Slime, where we're, opening it under the vLLM project to specialize it with the vLLM project, and ultimately learn and, for the benefit of the community and the benefit of vLLM, because Slime is such a great and interesting framework, but ultimately doesn't take a lot of upstream contribution. So yeah, we're sort of building on top of it, and currently starting with just a few people, building this out, trying different experiments, implementing advanced RL features like router replay for on policy MOE training. Yeah, so if this kind of interests you, this is a great chance to get in early at a new project with a few people working on it in vLLM. Should be a lot of fun. So, check out the blog announcing it, sort of talking about our plans and our hopes for it. Yeah, give it a star as well if you want. Next, I want to talk about some models. We had, NVIDIA Numatron 3 Ultra has been a highly anticipated open source model from NVIDIA. It's competitive with the likes of Kimi K2.6, GLM 5.1, Qwen 3.5. Yeah, so there's a whole blog on all the, inference optimization work, the RL work that was done. This model, all of the RL of it, which was done in Nemo RL by NVIDIA, was done using vLLM as the inference engine, proving that it can work at scale on GB200s and sort of the latest hardware. And of course, we love seeing charts like this where, of course, the model is competitive on an accuracy perspective, but when you look at the performance, it can be 2 to 3 to even 5 times faster than comparatively intelligent models. Of course, because the hardware vendor is going to know how to tune the models very well for their hardware. So I think it's a really interesting release, and of course, a great model made in the USA. So love to see NVIDIA investing in new models for the open source ecosystem to benefit from. So yeah, give that a read. And then yeah, we had a great launch yesterday for the latest model from Google. They've been releasing a lot with their Gemma 4 series, and the latest one has been Diffusion Gemma 4. And this is really interesting because this is the first diffusion large language model that vLLM is supporting natively. This is actually leveraging the in progress infrastructure with Model Runner v2. We found it to be actually really sort of elegant to implement this model in Model Runner v2 rather than in the v1 engine, which definitely gives some validation that it's a better abstraction and better structure. than what we had previously. And really, the performance just speaks for itself. This like type of diffusion inference is a completely different paradigm than traditional autoregressive inference. It actually predicts 256 tokens at once. Of course, it takes multiple steps to iteratively, denoise and validate, or like converge those tokens in parallel. But it results in over 1,000 tokens per second at batch size 1 on an H100, which is, just a crazy thing to think about. And so we're really excited about this model. It's also a very capable model, can do a lot of coding tasks, and has nice integrations with vLLM. So definitely check out the blog. There's a ton of great details in there on how it was achieved, especially to get to this level of performance on day 0. And overall, how a diffusion model like this, a diffusion large language model, it's still predicting text, works, and most importantly, takes advantage of new structures in vLLM like Model Runner v2. Next, I have a bit of, an update on the state of DeepSeek v4 semi-analysis, which makes the InferenceX benchmark. Sort of published an update after a month and a half since the release of DeepSeek v4, how vLLM and overall the open source ecosystem has improved performance and gotten DeepSeek v4 to work across. I thought it would loop. I'm sorry. Would work across a variety of both NVIDIA and AMD hardwares. So ultimately, going to the top right quadrant is better across interactivity or total throughput. And I'll stop it on the final frame. It's just a really nice thing to see that sort of all the fruits of improving the software over time. This is a video that's sort of going day by day on how vLLM is working across more types of hardware and constantly improving the performance of the same model, same workload, just by making the software better. This is like really great validation for what we're doing on our day-to-day and why we're sort of making the steps we're making every day in vLLM. So they have some great analysis in there as well for how this is happening and where the successful parts are in the open source ecosystem. So just a great shout out there. So with just some of the things that have happened over the past 2 weeks, I'm still going to spend some time on the vLLM release we actually had since then. This was a pretty hefty release. We had 459 commits from 230 contributors, 63 of those brand new contributors to the project. So love to see that. I would say the major highlights of this release are a lot of hardening for DeepSeek v4. Obviously, those iterative improvements I mentioned just before, a lot of those landed in this release, especially in terms of performance on AMD GPUs, particularly on speculative decoding for DeepSeek v4, enabling like full and piecewise CUDA graphs, and just general optimization work to make the ROCm GPUs more competitive with the CUDA GPUs. We've also been working on expanding the number of features that Model Runner v2 can support, and we've started to enable it by default for a few select model architectures, really starting with Qwen 3 dense models for now, and starting to expand slowly the number of models that can run on v2 by default, so we can start testing and exposing our CI and also users to start to battle test Model Runner v2 as it's getting closer to being enabled by default. We've also had a lot of improvements on batch invariance, particularly for quantized models, namely FP8 and MVFP4 on NVIDIA. We've had custom CUDA kernels, Cutlass kernels made for those precisions, and also made it work on new platforms such as Ampere GPUs or A100s. For speculative decoding, we've started working on a more sort of pluggable drafter infrastructure with the custom proposer backend. So hopefully in the future, there'll be more flexibility and pluggability in introducing new types of drafter models or drafter structures of models. We've also started work on an experimental Rust frontend Ultimately, the server process of vLLM is currently Python based. This is where a lot of tokenization happens, detokenization, tool parsing, reasoning, also multimodal processing for getting your images in the right size. And Rust can help with a lot of, and all these things are sort of happening on your CPU. And especially as we get into larger cluster scale deployments where you're serving 1,000 or like 10,000 concurrent requests on a single vLLM instance, we often need to duplicate the server and sort of have additional API server scale out. For instance, serving vLLM on like 2 nodes of GPUs, but then having 16 server processes because Python has a sort of threading model constraint. So ultimately, porting this to Rust will make the single-threaded case faster and also allow us to do more sort of native threading parallelism work inside of the server, and ultimately allow the CPU bottlenecks that we find in large-scale inference to be less of an issue. This is going to be a long project. That's why I'm giving it kind of a proper introduction. But look forward to it, and also please give it a try and see if you have some sort of simple, straightforward, text in, text out workloads. Give it a try and see if you see some performance improvements. You certainly should see at high concurrencies, and certainly let us know if you find any bugs. We've also been working a lot on KV cache offloading, building out the sort of multiple tiers with now secondary storage tiers. So not just offloading to CPU memory or between instances of vLLM, but to file systems now, to solid state disks, or even databases. Just a whole lot of performance improvements continuously here. We've also been hearing the community a lot, trying to push for Blackwell RTX improvements. That's SM 120 and 129. So your DGX Sparks, your RTX 5090s, your RTX Pro 6000s. We've been working with NVIDIA to add a lot of new kernels in order to better support the feature matrix of quantized model performance, especially on those platforms. We finally landed the PR for thinking token budgets and renaming or sort of renaming a reasoning effort to enable thinking to match up with some general API changes that are happening in the closed source APIs. Sort of last things to mention are sort of if you've been using MOE or linear environment variables to specify like the flash infer MOE or the linear kernel that's being selected, we've fully started to deprecate these environment variables and use the proper MOE backend and linear backend arguments on the CLI. So please give those a try if you're not familiar. That was a lot to go through. I'm sorry for taking up so much time, but now we're going to move to a sort of engineering spotlight, as Sasha said, our first one of these. As Sasha mentioned, Matt is a very active committer on the vLLM project, and he's been working on some cool stuff for sparse MLA, aka the latest DeepSeek models, and has a cool optimization to walk us through. So take it away.
Yeah, thanks. It's good to be here. As Michael mentioned, I'm an ML engineer on the vLLM runtime team here at Red Hat. And I'm just going to give like a quick talk about one of the techniques that we're using. It's in the works to accelerate sparse MLA via something that we're calling masked MHA. So just a brief overview in case you're not familiar with what MLA is. The key word in MLA is really latent here. So if you see on the left, that's kind of like a classic multi-head attention projection. So you have your hidden states, and then you have weight matrices to project that. So you have WQ, WK, WV, and you use those to project your hidden states into your query, key, and value tensors. MLA is what you have on the right. So you have a WQ tensor to get your Q tensor. But then instead of having separate K and V tensors, you just have a single WKV that projects into like a low dimensional CKV. So you just have one KV representation. And if you look in the bottom left there, you can see our hidden dim on like a classic MHA. The equivalent would be about 16,384. We're compressing that into just a dimension of 512. And so your KV cache gets to be about 57 times smaller. The reason that it's not 64 is because what you see in this graph here is a little bit of a simplified view. So it's ignoring stuff like rope, which has to be handled in kind of an interesting way in MLA. But if you are interested to see kind of like the full computational graph with all the details, I'll just plug my own little web app there at the bottom, which is like a nice tool for visualizing all these different attention mechanisms. Now, the interesting thing is that when you are doing inference, there are actually two different and equivalent ways to compute MLA. And the first is what we call MHA style. So in MHA style, you take that compressed CKV tensor that you made earlier, and then you multiply it by some up projection tensors. So you have WUK and WUV, that's a typo there. And then you get your normal K and V tensors, and then you compute attention MHA style like you normally would. And when you do this, each QK product is over the true head dimension of 128. The other way to compute MLA is what we call MQA style. So instead of up projecting your CKV, you're going to compress your Q into the latent space as well. And now you have your Q prime and your CKV, and you compute attention directly over CKV in this latent space. And the thing is here, now each QK product that you're computing is over your compressed dimension of 512 rather than the 128. And so what you're paying by doing this is larger matmoles, right? So you're actually each attention operation is doing 3.4 times the flops, but you are actually getting way less memory traffic because you're dealing with the compressed tensors rather than the full representation. And this pairs really nicely with the kind of like pre-fill decode split that we deal with a lot in LLM serving, because in pre-fill, you are compute bound, right? So you want the most compute friendly possible implementation. And so we use MHA style for that. You get the smaller matmoles, you have some more memory traffic, but because you're compute bound, you don't really care. Whereas in decodes, your compute bound, your data movement bounds, memory bandwidth bound. And so you don't really care that you're spending a little bit more flops because you have vastly less memory traffic. Now, so this is all standard MLA so far. DeepSeek 3.2 kind of built on MLA by introducing sparse attention. And to give you just a general sense of what that is, you can see at the top, let's say we're generating this sequence here. vLLM is a fast and easy to use library for LLM inference and serving. And so let's say you're generating that last token, the query token is serving. Perhaps you don't care about attending to all of the words in your context. Like the stuff that might not be as important. And so you can save on the cost of this long context by only attending to the tokens that are most important. Now, how DeepSeek v3.2 selects those tokens is kind of another discussion, but let's say you just have those tokens and you know which ones you really care about, and you're attending to just those. You can see kind of in the bottom left, a visualization, that's your CKV tensor from before. Really, all you have to do is pick out a few rows from that tensor to attend over. And if you visualize your attention mask on the bottom right, you can see that row at the very bottom. That's what you're doing for this decode, right? So you have your query token all the way at the right, and then there's just a few highlighted cells, tokens that you're actually attending to. Now, with pre-fills, the situation is a little bit different, right? Because now you're computing this entire thing, not just the bottom row. And so now you can't just pick out, for example, a handful of these tokens to gather into your shared memory on your GPU, because at some point you're going to touch all of these tokens, right? And as implemented in vLLM right now, we only have the MQA pipeline implemented. And so the optimization that we're doing now is to implement MHA, that MHA pipeline, but instead we're going to pass a mask, this top K mask into our MHA kernel that tells it which tokens to attend to. And we do this in kind of like a efficient bit packed way. And that allows us to take advantage of the compute savings of the MHA pathway. And so the result that we get is up to about a 2x speed up for the attention operation in this sort of moderate seq length band. So on the top plot, you can see the blue line corresponding to MHA and the orange line corresponding to MQA. You can see that as you get to longer and longer sequence lengths, you eventually hit a threshold around 7740 where MQA starts to be better. But below that, there's a region where MHA is faster, and it can be up to 2 times faster. Now, there's actually a second threshold down at the very bottom, very short sequence lengths, 136 tokens, but we can actually ignore that with a second optimization, which is that if I go back to this last slide here, if our sequence length is short enough, our top K is such that we're just attending to every token in the sequence. And so when we're in that kind of regime, we can just run normal dense MHA. And so for DeepSeek v3.2, that top K is about 2048. And so we don't even need to worry about that. So now we kind of break up our MHA or our MLA pipeline into 3 regimes. We do dense MHA for very short sequences, masked MHA in the intermediate regime, and then sparse MQA at long contexts. And that's going to give us nice speedups across the board. So yeah, that was just kind of a high-level overview of something that's coming down the pipeline for MLA. You should see it within the next release or 2.
Impressive, Matt. Nice job, man. Thank you.
Awesome.
You set a
Love
high
this.
bar for the first example.
Thank you very much.
Yeah, definitely. It's definitely a cool optimization. Yeah, well, with that being said, let's hand it off to see what's new in Speculators. Finn and Helen, take it away.
Hi everyone, I'm Helen and this is Finn. We're both maintainers of Speculators repository and we're very excited to present what's new in Speculators. Thanks for choosing us over the World Cup, and to make it worth the sacrifice, Finn and I are going to attempt something crazy today. Finn will kick off a live demo for training a Qwen3 8B DFlash model. Don't worry if you don't know what that means yet. And by the end of this presentation, we'll see how it performs. Finn, do you want to share your screen?
Yep, I'm going to share. Okay, hopefully you can see my screen. At this stage, we're going to kind of go over the details of the demo later, but at this stage, we just want to kick it off to show you guys that we're running this live. And so we've got on our right here, we have a vLLM instance running that's going to help with our data generation. And on the left, we've just started training. So we'll go into more detail on this later, but for now, this is running and we'll see how it does when we come back at the end. Okay, and now I can share. Ellen, do you want to continue?
Next slide. Yep. First, I want to start with a brief intro of speculative decoding. There are lots of large language model inference optimization techniques out there, like quantization, sparsification. Most of them trade a little bit of quality for speed. That's what makes speculative decoding very special, because it's completely lossless. The idea is very simple. You can see here in vanilla decoding, the whole process is very autoregressive. Every time we generate a token, we pass it back to the model, run a very expensive forward pass if your model is really big, and then generate the next one, and so on. So with 3 tokens, we're running 3 forward passes. But in the bottom, for speculative decoding, we are training a much smaller model that drafts several tokens in advance, in this case 3 tokens in advance, and the verifier only has to run 1 forward pass to verify all of them. We can see here it will only accept a token if it's equally or even more confident about it. So P's of here are accepted, but the verifier is not so confident about the token pi, so it generated the token by itself, cake. And in this case, we're only running one very expensive forward case for the verifier model, and potentially we can see a speed up for up to 3 times. Now let's zoom in a little bit on how the drafter actually drafts tokens in advance. There is one very important breakthrough, is that instead of taking in raw tokens as inputs, drafters takes in the hidden states from verifier models, and it kind of learns the inner thoughts of the verifier model. For some of the older techniques like Ego3, the drafter will auto-regressively draft tokens. You can see the little loop on the right. This draft model, if it's Ego3, will draft both and worlds in 2 different forward passes. But some of the new algorithms like pEagle and DFlash can now get rid of this cost as well. At this point, you're probably wondering how you can train a speculative decoding model by yourself. And Speculators library is exactly what you need. It's a unified library for training your own speculative decoding draft model, or convert a existing model, so that it can be directly served in vLLM. You can evaluate your newly trained speculative decoding model, and we make sure all the models trained by this library is directly servable in vLLM. And now going into updates. We have several very exciting updates that we would like to share today. Let's move on to response generation. The first new feature we add is response regeneration. This kind of solves the data quality problem. When you train a drafter model, you want to train on the data to match the target model's actual output distribution. But most public datasets like Magpie, UltraChat contain responses from different models. We observe for some models, there's a distribution mismatch between what the drafter learns and what the target model actually produces. So response regeneration should fix this issue. You pointed at the as this command shows, you pointed at a data set and your target model, and it spins up a vLLM server, takes the original user prompts, and regenerates fresh responses from your target model. Now your trained data is accurate. The draft model learns to predict what your specific target model would actually say and what not some other models said. So this should directly improve the acceptance rates. Now that we have good data, we can talk about which algorithm to use for your new model. Ego3 is probably the most mature algorithm we support in Speculators. The draft model, like we said, doesn't process raw input tokens. It operates on input from hidden states from the target model of different layers. These hidden states gets projected and passed through a lightweight decoder layer, and then LM head produce draft logics. This drafting is completely auto-regressive. It generates token 1, feed it back, and generates token 2, and feed it back, and repeat. And then the target model verifies all of them. We have a whole collection of models that we've already trained, and feel free to check them out on Hugging Face. And move on to pEagle. Naturally, it extends on Ego3's. Instead of drafting tokens one at a time auto-regressively, it predicts multiple tokens in parallel in a single forward pass, so it's even faster. Remember how we said Ego3 needs k sequential forward passes to draft k tokens? pEagle completely eliminates that. Now the challenge is that when you draft in parallel, positions beyond the first doesn't actually have the predicted tokens and the hidden states from previous steps. And pEagle solves this issue with a learnable shared hidden states that should fill in for the missing context. The architecture is a little deeper than Ego 3. Ego 3 is usually just one layer, but because we're missing some context, so we're making it up by having more layers for more capacity. One challenge we face is memory, because parallel prediction quickly blows up with longer sequences. pEagle handles this with caught sampling called conditional drop token sampling. The idea is very simple. At depth 0, you keep all positions, and for example, in position 1, you only keep 70%, and then you keep about 0.49 and so on. And we also have a minimum floor to make sure you don't drop too much to still have a meaningful learning. This should dramatically reduce memory, and pEagle models that we train are directly servable and supported in vLLM as well. And now let's move on to DFlash. DFlash is very exciting. It's most architecturally distinct algorithm. Instead of autoregressively drafting like Ego 3 does, we have parallel multi-depth prediction. It uses a small diffusion model, which is fundamentally different from Ego 3 and pEagle, and it generates an entire block of tokens in one forward pass. The key difference is that it uses bidirectional attention. Each position can attend to both the verifier's hidden states and all positions simultaneously in the same block. During training, similarly, we're seeing a memory challenge. Naively, you would want to predict a block for every position in your training input sequence, but that would be super expensive. And instead, we randomly select a sample of subset of positions as anchor positions and fill in tokens for each block. The model predicts entire block at once using bidirectional attention. Currently, we've trained a JAMA 430B model and a Qwen 3.8B model. Feel free to give it a try and let us know. And now let's move on to, last but not least, MTP. Oh, sorry. Here is a graph showing how our Qwen 3.8B DFlash model actually speeds up inference. We can see the intertoken latency has gone down, and we're seeing about 2 to 3 times of a speed up for a relatively small model like Qwen 3.8B. And what's good about speculative decoding is that it's completely orthogonal with other inference optimization techniques. So combining it with quantization, you can see in the dark red line there, we see even more of a speed up. Now, finally, let's move on to MTP. MTP is a little different because some of the newer models like Qwen 3 Next and Qwen 3.5 already ship with their own MTP head, their multi-token prediction head. And what we provide is that we can fine-tune this MTP head on responses generated by the model itself or domain-specific data. Everything else stays frozen. You're only updating the MTP head, which is less than 3% of the model usually. And the workflow in Speculators is simple. You convert the native MTP head to speculator format, fine-tune on your data, and then stitch the weights back, make sure they're servable and runnable in vLLM. If your model already has an MTP head, this is the easiest way to get started, and it's lowest effort to train your own speculative decoding model. Now you have a newly trained model, and you want to know how it performs. We also added a unified evaluation suites. It connects directly to your vLLM server. endpoint and measures per position acceptance rates and how often your tokens are drafted and accepted for each positions. And you can see where exactly your drafter is strong and where it might fall off. And for the full performance sweep, it uses guide LLM to benchmark across 9 different evaluation subsets that we provide. It automatically estimates the write output length for each subsets and then sweeps across requests to generate some performance data on latency, throughput, time to first token, inter-token latency. And we also added visualization tools. The graph that you saw earlier are generated by this evaluation suites. You can overlay multiple versions to compare them or do a pairwise speed-up analysis. Try it out, let us know. And last but not least, we invested heavily on documentation. We have this very nice, beautiful website, have comprehensive docs covering every algorithm for Eagle3, P-Eagle, DFlash, and MTP, like I just mentioned. And there's an algorithm decision guide that helps you pick the right algorithm for your use case. We also have 8 different step-by-step tutorials covering online training, offline training, response regeneration, evaluation, and serving in vLLM, each with time estimation so you know what you're getting into. This would be a great place to start, no matter you are trying to contribute or just like trying to get started. Now I'll hand it to Finn to talk about hidden states extraction and the exciting demo.
Thank you, Helen. Yeah, lots of exciting updates on the speculator side. I'm going to go a little bit back and talk about vLLM. And so we're working very closely with the vLLM team to make sure that we can support speculators training workflows using vLLM as a backend. So as Helen mentioned previously, we expect a lot of these models expect hidden states as inputs in order to train. And so we need a way of getting these inputs, getting these hidden states from the verifier model to the model during training. And initially we had an old system that used transformers and ran it live, but this doesn't work very performantly, and we wanted to use vLLM. And so we designed a system so that we could get hidden states directly out of vLLM into the training process. And there are kind of a lot of considerations that had to go into this. So we were quite concerned about memory usage. These hidden states are quite large, and so we need to be allocating space for them in vLLM while they're getting transferred. And also we need to make sure that we're not blocking the vLLM process in a big way or like doing something super inefficient. So this is the system that we came up with, the hidden states extraction system. And kind of how it works is we're making use of some existing features of vLLM. So vLLM already supported speculative decoding, like actually serving one of these models. And so the way this works is we pretend we're serving a speculative decoding model. So that's up here, this dummy Eagle3 model. And this fake model that we're serving, it gets hidden states from vLLM, like they get passed to the model using the existing pathways for speculative decoding, right? It's just pretending to be a speculative decoding model, so it gets those hidden states that it needs. And then the model itself, it can't directly save those hidden states because that would block the process, the vLLM process. It's all torch compiled and all that. So what it does instead is this fake model just inserts the hidden states directly into its own KV cache layers and uses the KV cache kind of as storage for the hidden states. And this actually works quite well because KV cache is allocated based on the prefix, and there's the page detention system in vLLM to kind of keep track of what KV cache belongs to what sequences. And we kind of need a very similar thing for the hidden states because we might have multiple requests. Some requests might not get get populated from scratch, right? There might already be existing data in the KV cache for prefix caching. And so we needed a system that was going to be able to work with all of that. And so by treating the hidden states as KV cache, we're able to, get a lot of those benefits for page detention and for keeping, like, tracking the requests in a good way. And then the second part of this system is we use the KV cache connector, which this is a system designed usually more for like prefill decode disaggregation. So for moving KV cache from one server to another, or offloading some of it to disk. But we're just using that system, which is designed to efficiently transfer KV cache data, and we're using it to now take out those hidden states that we've stored in the KV cache, and move them to disk or so, where the training process can load them. So that's the hidden states extraction system. This landed a couple months ago, and kind of as part of this, it has allowed us to kind of update a whole bunch of the training workflows in Speculators. It enabled, in particular, this online training option. So there's kind of two approaches to speculative model, speculative decoder training. Historically, people were doing offline training, this one on the right, where you have some data generation process where you generate a whole bunch of hidden states, you store them all to disk, and then you train on them. And so create your data set and train on it. And this is very simple. It works well. The challenge is that with a large data set, you are looking at like tens of terabytes of disk storage, for each model, for each data set that you're generating. And so this doesn't scale very well, and it causes a whole bunch of issues, needing to find places to kind of store these data sets. And so what we would like to do instead is be able to train, and as we're training, generate those hidden states kind of on demand for specific samples. We just send the text to vLLM and we get back the hidden states. And so that's exactly what we've implemented using the hidden states extraction system from the previous slide. And so that's what you see on the left. Now, we also still support offline training. So there are cases where this might be good. Like, for example, if you're doing certain experimentation or so, and you want to kind of run a whole bunch of tests all at once, you can generate your data once and then reuse it, as an example. So we support both of these, and we also support them in a way that's very fluid. It allows, like, they kind of use the same system in both cases, and the data format is the same in both cases. And so we try to match this as much as possible, to the degree where you can actually, we also support some hybrid options. So you could, in theory, do like online data generation. So you send your request to vLLM live and generate hidden states, but then rather than just using them and discarding them, you can actually save these to disk, and then on your second epoch, you already have all your data generated, and you could just load those. So yeah, we try to make this super robust and super flexible, so that it can be used easily. Yeah, and so now we're going to look at, we're going to see how our training job went and see if we can, yeah, kind of look through what training looks like for these processes. So as you can see here, it's still running. We have on the left here, this is our training process. We're outputting a whole bunch of logs. So, obviously training loss, but then also we have like per position acceptance or accuracies. On the right here, you see is our vLLM server. This is running with data parallel 2. So we have basically 2 instances swapping back and forth, and these are generating all these hidden states live, so that we can do online training. So we see all this here. I'm going to actually scroll up to the top if it's still there, because I wanted to show you what this command looks like. Sorry. Okay. So we have, here's our command. So we're running this on 2 GPUs. We're using torch run to set up our FSDP setup, and then we're kind of, I'm not going to go through all of these, but we're saving these checkpoints as we go to this folder here. And we're also running, I also want to call this one out, so we're running with track.io. So if you're not familiar with track.io, it's it's a experiment tracking system. And so we should be able to, if we refresh here, to see the logs from this running experiment. So yeah, here's our Qwen3 demo. And here, if we scroll down, we can see the accuracy over time. This is the average accuracy. We also see, these other metrics. So per position accuracy. This training job we're running, it's just on 5K samples. And I mean, as you saw, it's just running for 20 minutes. So it's not going to get the absolute best results. It's probably going to overfit to the data a bit. But we're hoping to see that we can still get some good results. Here we see our losses is going down. If we scroll down, we can also look at the validation results. And we see, per position accuracy is going up, losses going down. So that's a good sign. I'm going to go back here, and it looks like it's just wrapped up. We're saving our last checkpoint. And it's going to run the validation epoch. I'm actually just going to kill the job. So we should have, if I switch here, we should have now in this folder, we have the checkpoints we saved. We also have this checkpoint best. So this is a symlink to the best epoch. So it was actually epoch 3 in this case. And now we're going to attempt to serve these. So this is just serving the base model, Qwen 3 AP. And then down here, we're using our symlink, and we're going to serve the checkpoint that we just created. And so this is going to take a moment to launch, but what we're going to see here, so first off, you'll notice I'm not passing in any spec decoding related arguments. There are arguments you can pass in, but we actually don't need to use them, because one of the things the Speculators library does is it sets up this, it creates this custom config that vLLM can recognize, and it can automatically recognize that, okay, this is a spec decoding model. This is the verifier, so Qwen 3 AP, that we need to use with this drafter model. So all that information is stored in this config. So if I scroll down a little bit, sorry, hopefully it's not too hard to see, but we should see that we're loading both our drafter and the verifier model. And these will both get set up together and ready to serve with vLLM. So I'm going to give that another moment to launch, and then we're going to try to see running these two in parallel. So looks like they're both up. If I go back here, we have this is just like a simple benchmark suite. And this allows us to kind of just run the two models side by side on the same input. So we're gonna give this a try and see if everything works. Sometimes it takes a sec. So okay, this time it was a little bit slow to launch. I think sometimes we get first response jitters. Let's see. Yeah. So what we should be seeing here is that we're getting, if we compare these two, we're getting a slight end-to-end speed up in terms of also token throughput speed up. Now, that being said, our acceptance rate is quite bad. And so that's to be expected, given that we only trained this model for a very short time. But we should expect to see that this model is running a bit faster. And the kind of takeaway I want to give you is that this is not the best model that we've created here, but it is a model that we were able to create in 25 minutes during office hours. And if you train this properly, if you follow the tutorials we've provided, it's very easy to get started and to train speculative decoding models, and it's very easy to, I mean, if we're already getting like a 10% speed up, that's already huge, and you can get a lot more. We often see 2 to 3x if you train on your specific use case, if you fine tune the speculators and you train on more data and for longer. So yeah, hopefully you're all excited to use speculators, and we'll all go home and train speculative decoding models now. And I'll leave it with these last few slides. So yeah, please get involved, both in the vLLM community, also in the speculators community. We have regular SIG spec decoding meetings. We are also on the vLLM Slack. You can find us on either the speculators channel or the spec decoding channel. So yeah, please give it a try. Let us know if it works for you. Yeah, thank you.
Awesome. I know I always say this, not always, a lot of times I say this, but this is one of my favorite office hours. So very nice job, everyone.
Thanks.
Yeah, I think that was a great level of introduction, detail, live demo. I'm glad it was successful. Crazy that you trained a speculator within the live thing with metrics and everything. So yeah, very impressive guys all around. We're at time perfectly. Congrats on that as well. But we have some questions. I think overall, I think people have been doing a great job sort of responding to them. But are there any that, Helen or someone else wants to talk to directly, or people that want to unmute and ask?
Yeah, I'm curious if this is also able to be combined with X-grammar, so that you could have speculators that are also constrained in their output.
Yeah, so it is compatible with structured outputs in general, or a guided decoding. X-grammar is like one of the backends we have. We also have like L guidance, and I think some more. Yeah, the specific optimization I think you're referencing is what's kind of called, or at least I call, like jump decoding, where like if there's some, like the grammar is restricted enough that you could only generate like an open bracket, a start of a string, a close of a string, a comma, a new line. Then we just
that's exactly
take
what
those.
I'm thinking.
Yeah. Yeah, I mean, that's kind of orthogonal to spec decoding, and we haven't implemented that in vLLM, even though we could. Actually, recently someone tried to do it again, because it actually works as a speculator itself. Obviously without a model, which we have other methods. We have like suffix decoding or n-gram decoding that are sort of model-free methods of doing spec decoding. But basically the concern there is that the model is affected, like ultimately there can be multiple tokens that satisfy a given grammar, I guess. Like for instance, you can have a token that's like just a close bracket, or it can be close bracket, comma, and new line. And depending on like which one you choose, whether you choose like the, separate subtokens or like the composite single token, it changes the behavior of the model ultimately for future tokens. And that's something where, we're a bit scared, I think, to start choosing tokens for the model where if you didn't have the constraint of like trying to choose the optimal one, you're like, not following the model's reference behavior. And obviously with spec decoding here, we want to follow the model's reference behavior. So yeah, I think it's still something to explore. I think maybe I'll take a look at that draft PR someone posted again and see if it's easy to kick the tires on. But at least the structured outputs, if you're constraining the output of your model to some grammar for tool calling or whatever, and you want to also use speculative decoding, we want these things to work together, and they do work together in vLLM. Yeah.
Awesome, appreciate it.
Yeah, great question. Any other questions from people?
I think it's World Cup time. We're 5 minutes in.
Yeah.
Okay. Hear you loud and clear, Sasha. Yeah. Well, thanks everyone for taking the time to spend extra time with us and yeah, hearing about the updates. Thanks to Helen, Finn, Matt, Sasha as well. Great to see you. And yeah, hope everyone has a good 2 weeks, and we'll follow with you back up hopefully after some good games of football, soccer, whatever you want to call it. Okay, take care, everyone.
Bye, guys.